For this lecture, we will go over some of the various systems of measurements that is used in the laboratory, as well as the laboratory equipment, and we'll discuss a little bit about various reagents and how those are used. Of course, most of you are probably familiar with the metric system, so I'm not going to really go over this in a lot of detail. In the laboratory, most everything is done with the International System or the SI system, so most everything will be kind of calculated, or the terminology will refer back to the metric system. So just make sure you're kind of familiar with the various components of the metric system and the different terminology that is used within it. You're probably familiar with most of the terminology. A lot of what you're going to see, stuff will be measured in seconds or degrees Celsius, so most of this you're probably already familiar with. And if you don't really remember much about how things are categorized out, here's a good review to kind of tell you, like microns or micro is abbreviated with that little micro sign there. And what this does is it indicates that that particular value is times 10 to the negative 6 power. You'll see a lot of these various things used when reporting out laboratory data. So make sure that you're familiar with it, and we'll learn a little bit how to convert some of these things too. Of course, length is going to be measured using meters, so centimeters, decimeters, things like that. Weight or mass is going to be measured using kilograms, so you will need to be familiar with that measurement. Volume is measured in liters, so we will do a lot with milliliters and microliters. Those are going to be the most common that we're going to refer to, especially when we're measuring things for our mixing reagents for our various tests. We're going to measure things out in milliliters and microliters, so you do need to understand more of those two terminologies and how to convert one to the other. And of course, if we're measuring amount of substance, we're going to measure it in moles. The lab is kind of getting away a little bit from having to pre-measure things and mix up chemicals as far as in the medical laboratory field. However, you still do need to be familiar with it, because occasionally there might be some things that you do need to make up, and you need to be familiar with this. Temperature is going to be measured in Celsius. However, we do have labs that still use both. They'll use Celsius and Fahrenheit. So you may have to do some conversions there. So the equation for doing those conversions is here below, being able to convert Fahrenheit to Celsius and Celsius to Fahrenheit. And this could potentially be a good registry question where they'll ask you to convert one to the other. They may tell you that a particular specimen has to be incubated at 32 degrees Celsius, and so you may have to convert that into Fahrenheit, or vice versa. So that is something that you do kind of want to keep in the back of your mind of how to convert those. And you do also want to make yourself familiar with some of these more specific temperatures, like body temperature. I don't see as much referring to things as kelvins. However, Fahrenheit and Celsius you will see often. So you do want to be familiar of what body temperature is considered normal in Fahrenheit and Celsius, as well as freezing. Probably occasionally boiling, depending on the area of the lab that you're working in, because you will have to deal with these particular temperature ranges a lot in the laboratory, and not only freezing but normal refrigeration temperature, because you will that is part of your requirements, is to check temperatures and things for certain procedures to make sure that you are doing the test at the optimal procedure. So you need to be familiar of what's considered that normal range. There are some non-SI unit terms that are used in the laboratory, so this might be something like your time, minutes, hours, days, or pressure, millimeters of mercury. So you'll see this a lot like in blood pressures. And then, of course, reporting those SI units, you report both the number and the unit. So it might be 4.2 grams per deciliter, something like that. The unit expresses and defines the dimensions of the measured surface, so this could be something like based on the concentration, the mass, the volume. So this is a part of the laboratory reporting system. So when something is reported out, for example, at 4.3 grams per deciliter, so you have 4.3 grams of whatever substance per deciliter of amount of sample that is measured. Within the laboratory, you will use a lot of different labware. We often hear this now referred to as glassware. However, most laboratories are getting away from glass just because glass is more of a hazard. It's easier to break and easier to cause injuries or break open your gloves, things like that. It's just more of a risk. So most places are getting away from glass and using plastic type glassware or labware now. And you do still have some different tests and things that do require the use of glass, but like I said, most places are getting away from glass. And that glass, if you do still use glass, it could be made up of a variety of different materials. However, we still kind of refer to it as glassware or labware. And so all of that labware is designed to make sure that it meets certain specifications, to make sure that it delivers an accurate volume. And there are some different checks and things that can be done on glassware to ensure that. But we're going to talk about some of the different forms of labware and what some of the different things and components of it mean, and what you may use some of it for as far as measurements and things like that, which ones are more precise measurements versus something that you may just use it to mix something up in. And so each of these different things that you may use, especially like pipettes and things like that, they are going to be designed to deliver a specific way. And so that can be to contain or to deliver, and we'll go over this in a little bit more detail. But you do need to check the particular glassware that you're using to see what type of glassware it is before you use it, to know how you're supposed to properly handle that material. Most of it can be divided into two main categories, which would be containers or receivers. And so this might be something like your beakers or your tubes, flask, reagent bottles, anything that's basically just to kind of hold it or mix it. You're not really measuring with it. And then you have volumetric ware. So this is going to be something that you're going to use to actually make measurements with. And so this could be like your different flask or graduated cylinders, your different pipettes. So again, like I said, most things are going towards plastic. It is a little less expensive. It's more durable. And you don't have those hazard risks. But like I said, there are certain analytes that may require you still to use glass. But also something that has been found over the years is that there are certain chemicals that can kind of etch away at glass. And you may see this in the lab, in the student lab. If we have any kind of older glassware material, you can see where the glass itself looks more etched, kind of like it has some sort of hazy film over it, and it's just where the chemical has kind of broken down that glass component. Now, some of the disadvantages of using plastic could be that you have some leaching effect that goes on. So depending on the chemical that's stored in it, it can leach into that plastic and can affect if you were to reuse that container for something else. So a lot of you may be kind of familiar with this as far as at-home use. You have different things, gas containers and stuff like that. You wouldn't want to use a gas container and then rinse it out with water and then turn around and store your tea for drinking in, because that gasoline, that petroleum product, over time kind of leaches into that plastic, which in turn, if you were to use it, then that particular chemical could leach back out into whatever you're going to use to drink. So making sure that you know whether or not you can reuse something is very important in the lab. And then you also have some plastics that kind of allow for evaporation, so you can, depending on what you're storing and whether or not you want to prevent any sort of evaporation, especially with some of your different dyes and chemicals, especially the ones that are used in your staining techniques. Your different alcohols and stuff can evaporate very quickly. So you want to make sure that you ensure that they're stored so that you don't have that evaporation. So your glassware does have a little bit more of a higher chemical stability and clarity than your plasticware. But they're, again, depending on what field you're in and what type of work you're doing will depend on what type of glassware you're using. There are various types of glassware. And so they're all kind of made up of something a little bit different. So depending on what they're made up may depend on what you actually use them for. So for example, you do have some glassware that has like a little bit of a color to it, like an amber, dark, brownish type color to it. And so that particular glassware may be used for certain reagents that are very sensitive to light. So if you're storing a particular chemical that the light exposure can affect that particular chemical, then it's going to be stored in that darker glassware. And you will get a chance to see this in the student lab, particularly with your analysis. There are some spot tests or some confirmatory type testing that we can do that particular reagent is very sensitive to light, so we make sure that reagent tablet is stored in a darker container to prevent any sort of exposure to light. So you do have different containers, different types of containers, so you want to kind of be familiar with it and what its use is. So something like in Erlenmeyer flasks, and you see that down at the bottom, or a beaker, and of course those are trademark names, but we do still use them when we talk about that particular type of glassware or plasticware. But those are going to more or less be used more for your mixing of your chemicals. Something like that reagent bottle, where you can see it's got a stopper on it, may be more for storage. And then your things that are across that top row there, your volumetric flask, your graduated cylinder, or your volumetric pipette, those are going to be used more for measurement versus mixing and storing, because they do have a specific volume on them. So that volumetric flask may be for 100 ml, so it has a line on it there at the neck closer to the top, that if it's filled to this line, then it is this volume. So that one in particular will be 100 mLs or milliliters. So when we refer to a particular glassware or labware that is volumetric, then it has been calibrated to give a precise precision type measurement of that particular liquid or solution that is in it. And so there are things that are done to make sure that it is properly delivering the right amount. So there's some calibration procedures that are done. And some of your larger laboratories will actually, if they reuse glassware, they will check this periodically to make sure that that particular labware has not been etched or anything like that, or got some kind of coating in it that's going to prevent it from giving that precise measurement. And so again, you have your flask, your cylinders, graduated cylinders, things like that that were on the previous page. And then you got your pipettes. And of course your pipettes are going to vary a little bit from pipette to pipette. Now your pipettes themselves, they can be divided up a little bit more specifically. So you have volumetric, graduated, and serological. Now just to kind of explain the differences between those, with your volumetric pipettes, like the one that you have here at the end, what it is it's been calibrated to deliver a specific volume. So it only has one volume on it. And so that volume is marked by a particular line on it. So you would fill it up to that line, and then that is the volume that it would deliver. And then it also has a additional markings on it that you need to look for. So in other words, if it's to deliver or to contain. And then you also have graduated pipettes. So your graduated pipettes can deliver different volumes. So they have different markings on them. You can see those right here at the other end. And those particular volumes, you would draw it up to that particular mark. And then to take that a step further, within your graduated, you also have serological. And so with your serological, you have the measurements going all the way down through the tip, versus where your traditional graduated, it will have a particular marking on it. So you can kind of see how the numbers kind of look reversed. So when you're drawing this up, you're going to draw it all the way up to the zero. So if you were to only need 1 ml, then you would allow that fluid to drain until it reached that 1 ml mark. So you would let that fluid out, stop at the 1 ml mark, and you dispense how much you need. So you need to be very aware of the particular pipette that you're using to make sure you deliver the right amount of solution. So when we look at these in the laboratory, I want you to look at the various pipettes that we have available for you to use, and you need to look and see if that particular pipette will, as far as what you need to do to deliver that volume. Do you need to draw it all the way up to the zero? Is it calibrated all the way to the tip? Do you need to pay attention to the tip of it to see what exactly you need to deliver? Now, in addition to that, you also have your TD versus TC, so to deliver versus to contain. Now, your to contain pipette means that they've been calibrated to contain a specific amount of liquids. So they may not be necessarily calibrated to deliver that exact amount, but they are designed to contain a specific amount. And so that amount of fluid in that pipette can actually cling to the inside of that pipette. And so when it clings, it's kind of like a static cling. I'm sure you've seen stuff where liquid kind of clings to the side of that container. And so you need to look at those pipettes to see how they're marked. So these are marked with TD, to deliver. But if something is marked with a to contain, a TC, then what does that mean for you? What are you supposed to do with that particular pipette? And so when these are used, you need to make sure that you rinse it out with whatever solution you're pipetting into, to make sure that you remove the entire contents of that pipette. So an example of this may be when you get to hematology and you're doing your hemoglobin test. So when you pipette up your blood to put into your solution for that test, then you'll want to take that pipette tip and you want to actually rinse it off, because you will see when you do this procedure that the blood cells actually do kind of cling to the sides of that pipette tip. And so that pipette tip will, once you deliver that amount of blood, the blood that is left inside of that pipette tip is part of the blood that you needed for that test, part of that volume, that 10 microliter volume that you needed to do that test. So you'll actually rinse that pipette tip out and dispense that fluid that's in that tip to make sure that you remove all of the blood that's in that tip. If it's a TD pipette, which you see those listed here, These are calibrated to deliver a specific amount of fluid. So it could be graduated or it could be volumetric. And what you will do is when you allow those to drain, so you will use your pipette aider to suck up the amount of fluid that you need, and then you will take it to your next container and you allow it to just drain by gravity. And so it will just kind of drip out slowly or flow out of that pipette. And when you do this, you want to make sure that you always do everything in a vertical position, because anything that's tilted can alter that amount of measuring volume. So make sure you hold it upright when you're doing any of your procedures. And then once you've allowed gravity to drain that pipette, there's going to be a small volume of fluid that's going to remain in the tip of that pipette. And so this amount is left in there because it's already been calibrated to that particular volume. It's allowing for that amount of liquid that is left in it. So if you look at this graduated pipette over here to the side, let's see if we can erase some of this. So that graduated pipette tip over here to the side, you can kind of see where, I can get my cursor correct, you can see where at the bottom here, if you were to stop at this little area here, then you're going to have some that's left in the tip here. So you can see right there, there's going to be a specific volume that's going to be left in that tip. Now, if you're measuring 10 mLs, you're just going to take it all the way up to the 0, deliver your 10 mLs and stop, and then you're going to have an amount left in the bottom of that tip. So when you're looking at your pipette and you see the TD on there to deliver, it's to deliver a specific amount. That amount's left in the tip, and then you stop right there. That's your volume. However, if you have any that have this etched band across the top, what you're looking for with that etched band, and it's going to kind of either be some sort of painted on type band with some of your plastic ones, or your older glass ones, there is an actual etch in it into that glassware. You're looking for that band to determine if you need to blow it out. And then if you look at the one that's serological, you can see that it's calibrated all the way down to the tip. So anything that might be left in this tip from gravity, you do know it's going to need to be blown out in order to get that last little bit of volume in there. And so you want to make sure that you're looking at your pipette to see what it's required of that pipette. So with our specialized pipettes, we have micropipetters, and of course these are to contain. So like I said, if it's something that it's cleaned to the side, then you need to make sure that you rinse that tip out. And so your instructors for the first few procedures, we're going to kind of help you with this to understand when you need to rinse out a tip. Self-fill pipetters, you may not encounter this very often, but they're more of a capillary type action that is involved in these. So when you push your plunger down, it's going to fill up, and then your capillary pipettes, it's going to use like a capillary action where it sucks it in. So you'll get to use these when you are doing your hemoglobin hematocrit lab in your hematology courses. Again, make sure you know the difference between to contain and to deliver, and the pipettes that require a blowout procedure. So you'll take that pipetting aid and make sure that it fully dispenses what's left in that pipette tip. A lot of the errors that happen in the laboratories are due to improper measuring techniques. So you want to make sure that you are familiar with how to properly do this. So we'll have some labs where we'll work on these techniques and make sure that you are performing these techniques correctly. And we're going to go over those. You're going to watch some videos. So you'll get a lot of visual aids before you actually come into the lab. And again, as mentioned in other lectures, there's no more mouth pipetting, so you will use some sort of mechanical device for that suction mechanism. Now, like I mentioned earlier, you do want to make sure that your pipette is in a vertical position. Now, when you're actually trying to fill the pipetter itself, being at an angle is not that big of an issue, so you don't have to basically keep it upright perpendicular at all times. However, once you've sucked it up, you've got your fluids or your solution inside of that pipette, you go above whatever your marking is. So if it's 10 mLs, you go above that mark. Once you go above that mark and you remove your pipette from your container, so you're going to kind of do it like a straw. I'm sure most of you have played with straws as children or probably even as adults, where you suck the fluid into the straw, you cap it with your finger, and then you use your finger to control the release of that fluid in that straw. So it's kind of the same concept. You use your pipetting aid, you take it above the mark in which you're going to measure, you remove your pipette from the solution that you're trying to suck up and measure, and then you're going to wipe the tip of your pipette. Now, why are we wiping the tip of the pipette off with any sort of gauze or Chem wipe or anything like that? The reason behind that is you have liquid on the outside of that pipette. So just like it can cling to the inside, it can cling to the outside. You could have an extra drop that's kind of stuck to the end of that. Well, if that drop is on there and you don't properly remove it and it drops into your solution, then obviously you've got more in there than what you had planned for. So you have to clean the pipette tip off, the outside of that pipette tip, to remove any residual or excess fluid. Now, once you have got that volume in your pipette that's above your measuring mark, this is where it's very important that you hold it in that perpendicular upright position, because you're trying to adjust that meniscus level down to your measuring point, and then once you've reached that point, you keep it in that vertical upright position to allow that to dispense, and then you're going to drain it into whatever vessel you're putting it into. And you need to make sure if it's a TC or TD, most of what you're going to use is TD as far as your glassware type pipettes. And then if it has that etched band on it, of course you're going to use that blowout method. Now, something else you have to pay attention to is that meniscus. So I'm pretty sure that most of you are familiar with what a meniscus is, but what you're trying to do is actually get that meniscus to eye level. So if you need to lower your eye level to come down to that meniscus, or raise that pipette up a little bit to reach that eye level, you're looking at the very bottom of that meniscus. So that static electricity kind of makes it bevel up around the edges. We're not looking to measure at the edge, we're looking to measure at the bottom of that meniscus, so where that point meets that measuring line. So if you're measuring 1 ml and your 1 ml mark is this particular line right here, the bottom of that meniscus needs to be against that 1 ml mark. This is the way that these pipettes have been calibrated to read, so you need to make sure that you are reading it at that meniscus point. So there are a lot of pipetting techniques that we need to become familiar with when we're using automatic pipetters. So when we talk about automatic pipetters, these are devices that allow a rapid repetitive measurement or delivery of a predetermined volume. So if it's a 1 ml micropipetter, it's going to draw up 1 ml automatically. You don't have to look for a meniscus. The only thing you're checking for is if there's any kind of particular problems with that pipetter, which could create any sort of bubbles or anything like that in there. If something in that pipetter's hung, if it's gotten dirty, so things are hanging up so it's not measuring precisely, you're going to kind of keep an eye out for that. However, if it's running properly, you're just going to have quick measurements. You're going to pipette your solution, your 1 ml, and go to the next thing. So these have kind of helped to speed up that process where you're not having to manually pipette specific volumes anymore. So these have become very popular within the lab, but with these you need to be aware of how it works, how it dispenses, to make sure that you're properly using it. You have automatic dispensers or syringes that are used to measure cereal amounts, and these are usually smaller volumes. And so you're going to get familiar with how to use these, and there's a couple of different ways that you can use these. Now, when you're cleaning laboratory glassware or your plasticware, only the larger pieces of glassware are usually cleaned, like your flask, your graduated cylinders. Your smaller things are a little bit harder to clean. There's some processes that go through that glassware decontamination process. It could be a particular solution, it could be autoclave, things like that that are used to decontaminate them. But your glassware has to be decontaminated before you actually wash it, because you don't want to run into any risk of transferring anything infectious. If you do happen to break a glassware, make sure that you alert your professor and that you use proper techniques for cleaning it up. Try not to pick up, the larger pieces you can be very cautious with, as far as getting those up, or using forceps, tweezers, things like that. Your smaller pieces, you want to make sure that you're using some kind of broom, a hand brush, or dustpan to put those pieces in, and of course disposing of those in any sort of sharps container. We don't want to use glassware that's been chipped or broken, because it does increase the risk of actually injuring you. Plus, it may not measure properly if it has been chipped or broken. Laboratory balances. You will not see these in the student lab. Some laboratories do still use these, but since we've kind of gotten away from making solutions, you may not see this much. Some labs do still use these to calibrate their glassware, and so there's a procedure where they can use to measure out the volume and things like that, do some calculations to determine if that particular piece of equipment is measuring like it should. But these types of balances, the analytical balance, whatever you're measuring is put inside of the balance, it's put on the pan, the door is shut on it, and you use those knobs to do some weighing and calculations and various things to make sure that you don't have any kind of interference from any airflow or anything like that. So these are going to be very precise measurements that you're going to do when you're using something like this. Now, it could be that you do have to use some sort of weighing or balance in the laboratory. More particularly where you might see this maybe in blood bank, when you are having to do pediatric bags or split units, or trying to get the volume, weigh the bag to get the volume of that particular unit. If you're trying to set up a transfusion for a baby, there's only a specific volume that you can give a baby at one time, so you may have to measure that out into a separate sterile bag. But anytime you're doing any kind of weighing of anything, you want to make sure that your balance is free from vibration. So in other words, you don't want it sitting on the same counter that you're going to have a centrifuge, because that centrifuge is going to be vibrating that counter or that wall. So it's going to affect that balance and how it works. So you want to make sure that you don't have any sort of vibrations. You don't have anything, any kind of air currents blowing on it. You don't have anything that's blocking the movement of the pan. Anything that can potentially affect how that measurement is taking place. So when you get into the lab and you are working in the field and you have anything like that, you're going to be trained how to properly use these pieces of equipment. But just know that they are still used. It's not widely used, but there are still some areas of the lab where you may encounter having to use a balance. And of course, when you're weighing something, there are some particular practices that you're going to use. So just like if you were at home using your bathroom scales, you don't want to put a bag of flour on top of the scale and then get on the scale and weigh yourself, because it's not going to be accurate. So you need to make sure that that particular stage of that balance is cleared off. You don't have anything excess on it. You don't have any kind of grains of something spilt on it. You know, grains of another solution or mixture that you were mixing up that may still be laying on that scale. You want to make sure that it's been cleaned off before you use it. And you also want to make sure that anything you're weighing is always labeled. So if you're weighing something out, it's probably removing it from one container, putting it into another container. And so in the laboratory, make sure everything's labeled, because if you fall out, the person that comes behind you needs to know where you're at, what you were doing, what you were messing with. I'm sure at some point in your life you have seen some sort of scale, so that you know that there are different components of the scale. You have a way to level the scale. You want to make sure it's leveled. You want to make sure that there's nothing that's kind of hindering that movement of that scale. And you also want to know how to actually read that scale down to precise measurements. So if you ever do encounter a scale in your career, you want to make sure that you're trained properly, that you know that it's set up properly, and that you're reading it properly, because these are going to be intended for precise measurements. So you want to make sure that you're familiar with how to use it. A top-loading balance scale is going to have like a single pan on top. So somewhere where you might be kind of familiar with this would be if you've ever done any kind of measurement with food, where you may get like a household tiny small scale where you're maybe you're measuring out proportions of food or something, and you put on that scale. So this would be like a top load type balance, where you're weighing out something on that particular scale. So you may use this for smaller substances. Like I said, it could be potentially in blood bank where you're doing something like this. You will encounter centrifuges probably pretty much on a daily basis in your career. And so centrifuges are used to separate some sort of solid material from a liquid type material. So we use it in the lab to spin down specimens to separate serum and plasma from your red cells and your platelets, your white blood cells. You could use it to spin down a urine. You could use it to spin down other body fluids, to make some sort of sediment where you pack the cells down in the bottom of the tube. So when you spin something down, you have precipitate and supernatant. So your precipitate is going to be your sediment, whatever is spun down and forced to the bottom of that particular tube. And then your supernatant is going to be the liquid portion that is above whatever you've tried to condense down. So it's above that sediment. And so we will refer to these terms often with a supernatant. So if I tell you to pour off the supernatant, you're going to spin it down, you're going to get the sediment at the bottom of that tube, and then you're going to pour off the supernatant, that top liquid portion, because it may be something that we don't need, or it could be you're taking off that supernatant to test it on an analyzer where you're looking for glucose level within that supernatant. So you need to be familiar with those terms and what it means. There are a variety of types of centrifuges. You have centrifuges that sit on a tabletop, and then you have some that are pretty big, and they will stand on the floor. Some of your larger ones might be, for example, to spin down a unit of blood. You have refrigerated centrifuges, so these would be for test procedures in which that particular sample needs to be kept cold. Ultra centrifuges. These particular centrifuges spin at a really high speed, and they're really small. So this might be to separate out lipid particles. Cytocentrifuges, these may be used to force cells against a slide so that you can look at those cells on the slide. And then there's other centrifuges out there that have been adapted for specific purposes. An example of that would be a very small ultra type centrifuge that is designed to spin down a sample of platelets to be able to detect any sort of bacterial contamination in those platelets. The two traditional types of centrifuges used routinely in the laboratory are basically the conventional horizontal head centrifuge, which it has kind of like some little buckets attached to it, and when that centrifuge starts spinning, those buckets will sling out so that all of those samples are spun on a horizontal level, which is forcing everything to the outside edge. So if you ever think of a big circle, it forces it out to the edge. If you think about an amusement park ride, like something like the swings, as the swings start spinning, as that carousel type mechanism rotates, those swings will start to kind of fly out, and they'll fly out at an angle. But as you can imagine, if you were to speed up that spin, you would have people that were sticking straight out on a horizontal line from the top of that ride where it's spinning. Of course, that wouldn't be a fun ride, but you kind of get that concept that it would swing out. Then you have fixed angle centrifuges. So those samples stay at a fixed angle. So it could be about like a 45-degree angle that's kind of flexed outward, kind of like what those swings would be. Once those swings turn around in a circle and they get up to full speed, they're kind of flexed out at about a 45-degree angle. And what that does is it forces those cells down, and then you will, if you have a tube that has the gel separator in it, then you will see where that gel kind of sits in that tube at an angle. So the centrifuge speed is expressed in revolutions per minute, or RPMs. So your particular procedure may say spin this sample at 15 RPMs or 1500 RPMs. And so you would set your centrifuge for that particular force or the RPMs and spin your sample at that particular force. Now there are different RPMs for different specimen types. Some may spin a little bit of a harder spin, some of a softer spin. So it's going to depend on what particular specimen you're trying to prep for that. And so that will depend on what type of centrifuge that you use, based on what kind of sample you're trying to process. And so for a urine sample, it will spin different than a blood sample, and same thing with tissue. If you're trying to spin cells out of a body fluid to try to force it to a microscope slide, then you might use a cytocentrifuge. So you got to be aware of what your specimen is, what the test is, to determine what centrifuge you're actually using. And there are a variety of things that can cause malfunctions or errors when you're preparing samples based on that centrifuge. And one of those main things is making sure that that centrifuge is balanced. So when we talk about it being balanced, you want equal. You want whatever happens on one side, you want to make sure that you have that going on the other side. So if you have a centrifuge and you have various places where you can put that sample, you always want to make sure that you are putting those samples into that centrifuge where they will be equal. So wherever you place it at, you want to make sure that you also place something on the other side of equal value that is going to balance it out. So you always got to think about balance when you're using centrifuges. So if a sample tube is full, then the balance that you put on the opposite side needs to be equal. You don't want to put something that is low on the opposite side, because you're going to have more weight shift towards this sample. More force is going to pull it out. So when you put samples in a centrifuge that are not balanced and you start it up, that centrifuge is going to start rocking and rolling on that countertop. And you're going to have lots of noise. It could potentially break those tubes. It could potentially damage those seals that are inside of that tube. So you always want to make sure that it is balanced. You want to make sure that the top is secure. You want to make sure that the tops on the tubes are secure. You want to make sure that you don't have any way that a sample can splash out of that tube, create aerosols, and potentially put some sort of infectious agent into the air that you're going to potentially breathe in. You want to make sure that your centrifuge is clean of spills. You don't have anything that could possibly contaminate your sample, or something that could get you sick. You want to make sure that the maintenance on that machine is maintained. Most of your larger facilities are going to have someone that comes in and does the proper maintenance on those machines and does periodic checks on them. However, if you're in a physician's office, this may be your responsibility. So you do need to be aware of how to care for a centrifuge as well. So centrifuge should be labeled with some sort of biohazard indicator on it, because you are processing specimens that could potentially have some sort of infectious disease. So you want to make sure that those surfaces are labeled. You're going to do inspection of your centrifuge, make sure it's operating properly, make sure you do decontamination. So your lab should have some sort of procedure on these processes. You want to make sure that you've not spilled anything in it. If you spill something in it, you want to clean it up. If you do hear a tube break, and you will know when a tube breaks inside of a centrifuge, you can hear those fragments spin around and clink around inside that centrifuge. If that does happen, you want to turn that centrifuge off, you want to unplug it, and you want it to let it sit for at least 30 minutes to make sure that anything that may be in there that created any sort of aerosol does not get released into the air. If something does break, you want to make sure that you clean it up. You want to make sure that you use the proper equipment when you're doing that. Make sure you've got gown and gloves on. Make sure you're using forceps or tweezers to remove any broken pieces. Make sure you decontaminate the centrifuge. If it's something that's got the buckets in it, you want to take the buckets out. Make sure you clean those out, disinfect those. And if you think that it's caused any sort of mechanical error, make sure that you get that checked out by the appropriate personnel. Now, if by chance you are working in a lab that is handling any kind of biohazardous material that's considered like a bioterrorist type agent, anything that could be easily transmitted through aerosols or anything like that, you want to make sure that not only do you protect yourself, but you do protect others around you. So if you were processing a specimen that was suspected of some sort of bioterrorist type agent, and some sort of accident did happen, you want to make sure that you notify the proper people, that you get everyone out of the area, and make sure that that is maintained properly, and that it is reported to the proper authorities as far as taking care of that incident. There are different types of water that is used in the laboratory. And the water is more specific for the laboratory because there are things that can interfere with different analytes if particular water is used. So that water is run through a filtration type system that removes any sort of inorganic or organic impurities that could be in that water that could interfere with that particular test method. And so if you are doing a particular test method that requires a particular type of water, it's going to tell you. It could be specific as to distilled versus deionized water versus tap water. And so it will alert you, that particular procedure will alert you of what type of water is required for that particular procedure. Of course, type 1 reagent water is the most pure water that we would use in the laboratory. So just keep that in mind, that there are some procedures that may require a particular type of water to use in that procedure. Type 1 may be used for preparing various standards, buffers, controls. It could be used in your electrophoresis procedures, your toxicology screenings. And so with this water, it's usually produced on demand. It's not something that is stored. Type 2 is for qualitative chemistry procedures, and a lot of your procedures that are done in hematology, immunology, microbiology, or basically any other area in the lab. So it's going to be for your qualitative type procedures. And then type 3 may be used for some qualitative type procedures, but this water source is usually prepared a preparation of your type 1 or type 2 water, and it may be used for things like washing or rinsing your laboratory equipment. Any glassware that you use in the lab, it's usually that final rinse is going to require you to rinse it with a type 1 or type 2 water. So you wouldn't be using tap water from the sink. You would use something that's been filtrated. If you think about tap water from the sink, if you're using something that has gone through any sort of a filtration system from a public water source, you do know that they use a lot of chlorine and stuff in those waters. So that chlorine could affect the particular laboratory test that you're doing. So that's why using a water that's been filtered and remove things like that, like your type 1 or type 2 water, that is used so that you can remove any sort of contaminants that may be in that water supply. Now, part of your quality control checks in the laboratory is to make sure that your water supply that you're using is a supply that is free of any sort of contaminants. So some of the testing that might be done on your water supply would be getting a sample of that supply, checking it for any kind of microbial contamination. So your microbiology department might actually culture that water supply, make sure it's not growing anything. You could have various testing that you might have to do on it periodically. You may have to send it to an outside testing facility, or it could be something that you could do in-house. So depending on the test that you're using and the type of water that you need will depend on this type of stuff. Depending on what your particular water is will depend on how you store it. So you do need to be familiar with that with whichever laboratory that you work in. And you're basically just kind of preventing it from any sort of contamination through any sort of outside chemical source or microbes. The purification of water process can be done by a couple of different ways. It can be deionized or distilled. And again, however your laboratory chooses to do this, the laboratory that you work at, will be dependent on the particular type of test that they do. Now, occasionally we do still need to prepare some sort of reagent or material in the laboratory for use. And if we do, it should come with some sort of procedure that tells you what's needed to reconstitute or prepare that reagent. And so you would definitely need to read those instructions and make sure that you're using the proper equipment to measure whatever it is that you need to use to reconstitute. So a reagent is defined as any substance used to produce a chemical reaction. Now, this could be a reagent that's required for a particular test method, or what we most commonly have to do in the lab is reconstitute reagents for various kits that we get for particular test methods. So you could get a kit of reagents for a particular chemistry test, and within that kit it gives you the material that you need to reconstitute or to dilute out and prepare the solution for that test. Most of what you're going to use will be some sort of deionized or distilled water to reconstitute reagents. However, if a particular test method requires a specific buffer or anything, it will come prepackaged in that kit. And just so that you are aware, there are different grades of chemicals. There's an analytical reagent grade, a chemically pure grade, a USP and NF grade, and a technical or commercial grade of those chemicals. So depending on the particular laboratory test will depend on what particular type of chemical that you are using. And of course, any chemical reagent that is used in the laboratory setting does need to be listed in your chemical hygiene plan, and you should be aware of that particular chemical that you're using. If you do run into any problems or issues with it, you do need to be aware of the SDS sheet, where to find it, and be familiar with any hazard that may be associated with that particular chemical so that you're aware of how to handle it, how to store it, how to dispose of it. And so these are things that should be communicated to you when you step into a new role within a laboratory facility. And you do want to make sure that you know how to properly store that chemical. So you want to make sure that you're always reading the labels, you're reading SDS sheets, you're being familiar with that reagent or that chemical. It could require refrigeration, it could require being stored in a freezer, it could be required to be stored at room temperature. So you want to be aware of what the storage requirements are for that particular chemical. Acid and bases should be stored separately in some sort of well-ventilated storage cabinet. Anything that's flammable, of course, needs to be stored in the proper cabinet, as well as all these things need to be labeled with their storage requirements or any kind of specifics on it, especially if it's something that's flammable. And so when we're using chemicals and stuff in our student lab, you do want to make sure that you're adhering to the requirements that your instructor tells you. So if it's something that should be stored at a particular temperature, or after we're done using the reagent, if it's to be stored in any sort of particular place, that you are making sure to return it wherever it is required to be stored. Make sure that you have access to any sort of reference material that you may need for a chemical or preparing that chemical. Be aware that the concentration of the solution is dependent on whatever is in that solution. So whether it's a solute that's in that solution, or it could be based on the buffers or the pH level of that solution. In preparing any sort of reagent, you want to make sure that you're aware of how to properly do that. So it may tell you to transfer this solution into this container. It will give you a detailed description of what to do, so you need to make sure that you properly read that. It may tell you to pour all of solution A into solution B. Whatever that procedure is, you want to make sure that you follow those directions. Or it could be that you're dissolving a dry solution into a wet solution. You want to make sure that anything that you prepare, that you properly label that container. And so this is usually going to be what's in it, how long is it good for, the date that it was prepared, who prepared it. All of these things should be on anything that is mixed up, as far as mixing one solution into another solution and preparing something. You want to make sure that everything is labeled with what you do. And this is with anything in the lab. A reagent should never be placed in an unlabeled bottle or container, because if you don't know what's in it, you don't know how to handle it. You don't know how to properly store it. You don't know not to mix it with this solution. You don't know how to dispose of it. So if you find anything that's unlabeled in the student lab, make sure you let your professors know, so that we can kind of look into it. But again, anything that you do in the laboratory, even if you're drawing up some water to use to do a particular test, you need to make sure that that container is labeled that is water. Before using any kind of reagent in the lab, of course, you want to double check yourself. You want to look at that label. You want to make sure that you are using the proper reagent. You want to make sure that it's not expired. You want to make sure that if it is a particular kit where you're not to interchange controls from one kit to the next, you want to make sure that you're using the proper controls with the proper lot number of the kit. So you're going to check those lot numbers and things. A lot of your labs will have some kind of reagent log, which you will log all your lot numbers, expiration dates, things like that. You do have to keep track of these things. If you're ever to run into any sort of problem with your testing, You need these logs to be able to look back at lot numbers to find out, okay, was there a particular time when we started having false positives? Is it due to this particular lot number? What date did we open these controls? So you're going to have on your bottles, if you open a new reagent or you prepare a reagent, you're going to document on there the date that you opened it or the date that you prepared it, because that's part of your look back process. You may find that you started having errors and you can trace it back to a particular lot number of reagent, and you may find out, okay, this person prepared this on this day, so something happened with this particular lot. So maybe every patient that you tested on that lot, you need to pull their records and make sure that you reported out values that were not false. So keeping track of all of this detail somewhere in the lab is very important so that you can do troubleshooting type processes. A lot of your reagents do come already made, however some of them you may have to prepare yourself, so just be aware of those with anything that you're using. There are some special kits that may require specific preparation, so you want to make sure that you look at the requirements for that particular kit. Whatever those requirements may do, your laboratory is going to have some sort of particular procedure set up for those kits, so you want to be aware of those rules.